Yeah, let's begin. The topic for today is on sequential modeling. Yeah, actually, this is more traditional sequential modeling, which I want to emphasize this a bit before we move on to the modern transformer or attention architecture. Because for this you will see why it works or why it doesn't work. Okay, so when we talk about sequential modeling, what I refer to here is in terms of the RNN, recurrent neural network, and long short-term memory, LSTM network, okay, and also GRU and other with similar architecture. Okay, this type of model has been used in deep learning for quite some time. It has been used to create create the language model even before the era of large language model. So if you think about generative model in a way that try to replicate the sequence of things that is happening using probabilistic method like Markov chain, Markov model, I would say that you can trace back to very early 1990, 2000. There are quite a number of papers, quite a number of developments on sequential modeling to model different things. Models language, models time series, use it to model events, log, right? Many things, right? But sometimes it will be in forms of, say, a hidden Markov model, conditional random field. Right? There are those names that state that you use the hypothesis of sequence modeling, but you are trying to implement it in a way to capture the variations inside each state. So there are certain assumptions that are differences between different models. Okay, we are not going to delve into the detail of those specific models, but what we will look at would be the use of recurrent neural network or the sequential modeling like this in order to capture the language model. How does it work? And then we will try to also simulate that out as well. Okay, why are we considering sequencing, modeling the sequence? There are a lot of real-world data that are in sequences, if you think about that, right? And that might be one of the reasons that when people say that, oh, if you can model language, then you can capture a certain general intelligence, which for this moment we know that it might not be enough. Right, that it can certainly capture patterns and then extrapolate from the patterns, but whether or not it has generalized the pattern as knowledge and make use of that, still questionable. What we have right now is more like the autoregressive context window based chatbot, that there are context window, you put chunks into context window, and then you expect it to respond in a certain way. Right? But we will see about that later on. Maybe there will be like accumulation of knowledge. You might see it in the AI development soon. Right? Okay, so there are a number of data types that that are inherently sequential, like text. You have sequence of characters, sequence of words, right? There is the speech data that you have the change of spectrum, waveform over time, or time series that you have stock price, sensor data that change by time, DNA or protein sequence, or even user behavioral logs. And all of these are sequence data. And in order to generate those sequence data, you need to have the model that are able to capture sequential variation. What is that? Right? There is a very, I'm not going to go back to the Markov assumptions, right? But in the early day, to capture the type of sequential variabilities, one might model it as the Markov chain, right? That current states depends on previous states, okay? Or you can write it like this. When we talk about generative model to do to generating probability, you're trying to create or find the probability of the next token given the previous one. Okay, the token can be the word, it can be values, it can be multiple things. And then once we obtain this probability function, probability distribution, then the generation process is simply the sampling of this function. To do the sampling of the function, and then we will have the value out. The sampling process will be stochastic. It must not be deterministic, right? When we know that stochastic means you are doing sampling for the current token. Then if you are doing the sampling for the next one, right, it will the properties of the systems will change once you move on to the next token. This way of sampling of the autoregressive generation it is actually the same framework that is used in the current generative pre-trained model, the GPT model that we see in the ChatGPT in the current version of the language model. So basically, the model will have to predict the next token and then use that in order to predict the next one to generate the output. That means you start with starting of the sentence and then trying to predict what should be the next likely token, and then use that next token to predict the next one, and so forth. Okay. For the current generation of generative AI that we see, quite powerful one, they model token in multiple layers. Like some might be at the next word, next token, but some might be the next concept, the next 5 tokens. Okay, so there are like multiple layers of prediction, and they use those as, I would say, the embedding or the predicted concepts that should accompany in order to generate what should be the likely output. Right? So there are like the way that has been done is to create a sequential model and then predict the next token. This image on the right-hand side, we have the dog set on, and then what would be the likely next word. The language model has to predict what should be the likely next token and pick the highest probability. Actually, not pick, sampling from the output distribution. The highest probability will have higher chance to get picked. And then we attach that as part of the input and then performing generation further. Okay, so think about it like when you type into Google search, and then it prompts you with the next keyword that you should choose, and then you kind of choose one of that, and then let it goes on like that. So that's how it worked there. Okay, now if we look back to the last lecture on generative AI that we studied, the last lecture was on latent representation. Right? We learned about the latent vector C. Right? But instead of that, because in the latent vector like that, you can see we can create the latent vector by compressing image into lower dimension, right? And then trying to expand it back with kind of having representation that can discerning different characteristics from one another. But to make it work in sequential model, it is now not just compressing one image or compressing a set of image to be at a lower dimension, but we will move on from the fixed latent vector to be something like the latent state. Right? That means we would have the state of the model that represent the variation, right, of the text that is captured. So in the early generative model, we have C sampling from the distribution of noise, and then This is representation of the latent vector space that we have, right? And once we kind of add and subtract from the vector C, we would have the result that is that have certain representation. Like in VAE, we have subtract face with glass, male with glass, with male without glass, like that, and then trying to add them up to be the next one, having the specific meaning. But in the sequence generation, now we are not really having that types of latent representation, but we would have the hidden state. This hidden state will evolve, right? It will change once it receives certain token. The value inside will change accordingly, so that it allows you to remember things as a sequence. That means this function will have to be quite complicated, right? So that it will be able to remember. The mapping function here, right, it has to remember if this sequence coming in, what should be the next potential word. So it will be very, very complex, right? And then for each step, we can have the probability of x times t plus 1 given previous x as the softmax of multiplication between the hidden state and the output conversion from the hidden to the output multiplied by W. Okay. In terms of fuller mathematical construct of the sequential model, I will probably not talking about it here, but we will see how it works and then go to implementation of the language model. And your job for today will be to create the language model based on RNN, which is easy and not work. It's easy. You need to give it a lot of time for training, not very efficient. Wait for a long time, it kind of almost work, but probably not work. Right? It can do some simple thing, but not very complex. Like it will learn the structure, but to make it able to really generate the output that looks really like the input. Like what we use is Wikipedia to make it do that, where it will be really hard. Wait for a long time for the training process to be done. And also the model complexity has to increase as well. The one that I use in the lab is quite rudimentary in terms of the model itself. Okay, right? Okay, we are going to do this, right? Have the function that take in ht minus 1, previous vector. Okay, when you think about it this way. You have state vectors. Okay, and you have input of that token vector as well. Put them into a function, it predicts what should be the next state. And from this next state, you can then decode it using W and then softmax to have the highest probability on what token it should be, right? However, X, right? There is a problem with X. What type of token that we should use for X, right? This is quite problematic. Why? If you look at that, suppose we use a very naive method by encoding every word as a one hot vector. What would happen? Cat would be there, 0, 0, and 1. Dog, also 1. Hotel, also 1. However, if you look at the distance between vector, right? Look at the distance between these two vectors. You will get square root 2. This as well equal to the other one. Cat should be closer to dog when comparing to hotel, right? So that means encoding it this way is not good, right? It doesn't convey any meaning at all. But we are going to do it anyway I think, yeah, in the first example, I did use one hot, probably, or not. Let's I don't remember that. The collab is at the end. Um, right. But they should have a certain similarity embedding into the vector. That's why they call that word embedding, right? Embedding the meaning into the vector. Um, so embedding would solve that. Word embedding or word to vec, the idea is that instead of doing one hot directly, you multiply the one hot with word embedding lookup table, word embedding matrix. Then you will get E. Then E will be the representation of that word. Okay, so this would be like a lookup table. If you have the word cat, it should be that vector. Dog, it would be that vector. And then when you compare one with another, then it should reflect some semantic like male, female, like this. Man, woman, lion, lioness, or this Germany, German, China, Chinese, like this. That they are like equidistant when they have similar meaning representation when you compute the distance between them, right? And the structure can be used as well. So in a way, word embedding will now be the latent representation of the meaning, right? That you convert them into another domain to have a better representation of the meaning. When I'm talking about latent, I'm talking about something that is latent means hidden, right? Something that is hidden inside the representation. So what we are talking about is that more like it's like you are trying to encode the obvious into a sequence of words that have a better representation than just the word itself. And you can do the semantic stuff, right? Add, remove, subtract, like that. And how do we do that then? We need to have embedding matrix. This embedding matrix can be looked up, put in X, and then you have ET. This should be something that embedding matrix should look like. It will have some real value in there, no meaning in each values. And then you can, well, if you use function like in GenSim, there's like word to vec, right? You can just put in token and then it give you vector in that word to vec. But how does it work? Let's see, I think I have slide here. Okay, and once you encode it into the latent space, performing something like cosine distance, which will see the alignment of the vector, will give you the result that looks like this. The one that have the same topics, the same concept, will be closer to the other one that have different concepts. So in that case, it encodes certain meanings into such word. Okay, and this is cosine distance. Now, how do you get, this is still word vector, right? Having one hot multiplying by lookup, then you get the value. Then the word that have similar meanings like elephant, lion, tiger, they are closer to one another. But comparing to some other thing, it will be far apart. These are from principal components of 300 dimension word vectors. Okay, how do you get those? For now, you don't really have to do it by yourself. There have already been the study and the training of the word vectors if you want to use the existing one. But if you want to have like additional token that have not been trained yet, you probably have to incorporate the embedding into the training process, or if you want to fine-tune the existing one. But here, Mikulov in 2013 has published a paper, a framework on learning word vectors. And it works with, you need to have like large corpus of text, then every word in a fixed vocab is represented by a vector, so you change the word into a vector. And then going through each position, and then you have a center word C and context word O. You are essentially trying to predict what C should be from O. Okay, so trying to predict that, and then adjusting the word vector to maximize probability. So it works like that. There are two ways. I think the one that is quite more popular would be the second one here. The first one is that you have contextual word, and then from these contextual word, you trying to predict the word WT. This is called SIBO. I don't remember the abbreviation. Contextual center something. Yeah, I don't remember the full name, but the idea is to predict the center one. You can imagine, right? Predict the center one. And then skipgram. Skipgram is to use the input and then to project and then predict what should be the authors around there. Okay. Okay, let's move on. So this is how it works here. But in training, you are not really training, well, this is the concept, but you are not really training it to predict this word. What you will do is that you will pair a word here. You will pair the embedding of this word with the embedding of the contextual word. And then if they are in context, then you predict it as 1. If they are out of context, then you will predict it as 0. Then trying to just train this binary classification of being in the same, and then train the word embedding vector. I think I have the diagram here. Yeah. So this is how it actually works. You have the word I and word J, and then you have the embedding, which will be trained. And these will be trained, and then have them together, do the dot product, and then if they are in context, the output should be 1. If they are out of context, the output should be 0. In context means something similar. And then just keep training this to have the representation. But in order for the word to work, right, they have this, that is the likelihood function, that WT plus J given WT and the model. So it is the word given WT, these are like the contextual word. So this is the likelihood, it has to be high. The loss function, right? Log loss here. And then not likelihood, I think it's the loss function of the probability. And then take log minus here in order to make it compensate into to be negative log loss. Yeah, and then training based on this one. Well, it would be the minimization of this J theta, right? And then you will get the embedding vector, right? But in order for that, you have the objective function. If you look at this objective function, it has only the positive side. That is, if you pair them together, and then if they are close to one another, it will have high value, right? But in order to also having the negative side in the skipgram, like if you draw words from outside the context, then you need to add this noisy target in order to have the negative sampling in the loss function. So it should be closer to the context one. It should be far apart for the out of context. Right? So, and then by optimizing this, you have the word vector as a result in Mikolov study in 2013. And for this one, you can, if you, this is the comparison in PCA. One side is the country name, the other is the capital city. Okay, so this is the encoding part. Instead of representing the word as one hot, you can representing it as the embedding vector to have a better representation, have more meaning encoding into the vector. Right, now generation process, right? So encoding into what it has a certain meaning, but still what mechanism would be used for it to remember, right? Because right now we want to have a model that is able to capture patterns. What model would it be for this one? Okay. Neural network, the usual neural network is that when you have input, pass it through the network, like in the feed-forward network, you have output. So this work in one-to-one mapping, one version of input, one version of output. This is like vanilla neural network. Now there are different type of network. The network that can evolve, that means this is like vanilla neural net. For the RNN, the recurrent neural net, the green, you can see the green version here, giving it one input and then it will change the state, produce the output, and change the state and produce the output. This is one-to-many mapping. The task that is like this one would be image captioning. Right now it is known as multimodal because it is now trended together. But back then it was like, in order to have image translate into description, you would have an image model like CNN, ResNet, and language model, right? And then you have text in company with image, and then train them together, kind of like transfer learning, fine-tuning it, so that one image encoded through the network would produce many tokens, the description. So this is in the word image captioning. Many to one, you can think about this as having a sequence of words coming in, having just one output. The model like sequence classification, right, intent prediction, the chatbot try to perform, sentiment analysis, that belongs to this type. Okay. And it's funny, right now, sometimes we are trying to use LM to do this, right? Even though LM itself is more of the many-to-many, but well, if you really want to just detecting the class, use LM is good in a way that it has auto knowledge encoded into that as well, beside that. So, but just want to let you know that actually there is, you can create a sentiment classification using the sequence and then just map to the class. The problem with this model, if you were to train it yourself, would be that, oh, actually, you can just use LM, right? And then having one output, that solves the problem. Right? Not, you don't need like multiple sequences, pull it out and have one output as classification, fine-tune it, then you have a good model for prediction. Never mind, but we are not into, we have to kind of focus on generative one, not, this is more of discriminative, trying to classify the token. Okay, it can be this, this many-to-many mapping. You have many input coming in as encoder at the earlier part, and then you have the decoder at the latter part to produce the output. This is, I think, the original design of language model. You have encoder, and then you have decoder. And machine translation people work on this for quite a long time, and then you have language model replacing everything out there. Then lastly, in the many-to-many that align with one another, like in video classification, you need data as frame-by-frame processing. So you need to have a state evolve throughout the frame. And right now, the video model, some of the video model have to keep those synchronization like even finer detail than this one. Okay. So the one that we will focus on today would be this many-to-one, right? And that actually putting one in and then using the output to feed as the input. Recurrent neural network. In the recurrent neural network, you have X as input, you have the parameter theta, and then you have the previous edge t minus 1. This is the previous state. Then put them through the function, you get to ht. What is this function? Okay. For a normal recurrent neural net, this function is just some multiplication of weight and addition of weight. Okay, let's look here. Left-hand side, it shows you the representation if we will write it into as a recurrent model. H can evolve right, through multiple iteration. You have X coming in. Then that means xt minus 1 putting into the state ht minus 1 will progress the state ht minus 1 to ht. And then when it receives the next token, it will move the state to the next one, right? So this will change the latent vector inside the model, the latent state, right, from previous version to the next version. That means there must be some types of weight, some type of multiplication, some types of thing that will be done here, function f. That will change ht. That make it able to produce the output, because we are talking about something like, okay, after this one, it should produce the output, right? One by one out here. That means in order to have variability above here, there has to be some types of weight that capture the change of the state down here. Okay. Okay, so that means HT depending on previous sequence and depending on the state. Right, and once that we have that, we will then have, instead of the state alone, we will use the state HT to predict the output vector, right, or at some step. It can be at the end, it can be at every step, depending on the task. For generative function here that we are talking about, it would be for the next words, the next one that we will use, right? So how does it look like mathematically? ht minus 1 is the old state. You have the input vector coming in, and then the function here, f, will have the weight parameters w. Right? This parameter w represent the change of the old state and x into the new state. Right? This is what is called recurrent formula, because the new state depending on the old state. Here's how it works. From this function, if we were to expand it down, inside here, we would have ht minus 1 multiplied by whh. This to represent the dimension that it, suppose that h is 64 values. I suppose h is 1 times 64 as the vector. Then whh has to be mapping from h to h. That would be 64 times 64 times with ht minus 1. Okay, and this wxh times xt, this will transform the vector x into the dimension h. Right? Think about vector multiplication. In vector multiplication, when you multiply vector, right, you would map this dimension with this dimension, and then you will get the new height like that. So that's usually the case when multiplying the row to the column. And then you get the new dimension, which is the same dimension as h here. And then adding them together, passing through the activation function, tan h, which have both negative and positive. You have ht as the latent representation, right? Latent state, right? As a state of the RNN. And we have w as well, why. This would transform from h to dimension of y, and transform ht to dimension of y, then you have yt. Very simple, right? So that means you have three metrics to optimize. One is transforming from previous state to the next state, capturing transformation. The others representing the transforming, the importance of x of that state. And lastly, this one would translate from h into y. Okay, so if we use the notion that we often use nowadays, we would have first W here as encoder, the last W as decoder, and inside here would be, well, it would be state transition. For now, it would be state transition from one state to another state. And so you can see different role, right, of different metrics that are used in this model. Okay, this is the same thing. W and U and V are the same that I already talked about. We have here producing, and then after that, map with V, you have O. And then comparing to Y, then we can calculate the loss, and then use this loss to optimize the network here. So how does it work when you compute for the token? Start with H0 and X1. Fetch H0 and X1 to this bunch of W, you get H1, right, computation. And then get H2, H3, and so forth. And then each of these would have output Y1, Y2, Y3 to YT. And then from that, we can compare the output to the actual output and then feedback the gradient to update each step. Right? You have loss function, then total loss, and then feed them back. These are auto model. This is many to many. If many to one, that means you have one at the end, not for generative model. If one to many, you have one and you have many output, then you can have loss function similarly. Okay. And this encoder decoder, you have one as encoder and the output is produced at the next stage as decoder. If you look at the paper next time when we talk about a transformer model, you will see exactly this. You have one part as encoder and the other part as the decoder part, and that decoder part is the original GPT-3 model that is in the early day. Okay, now how do we apply RNN to generate sequence? Okay, we will look at the code later on. But let's look at how it works first with the simple explanation here. We have input character. Suppose that we encode the character into just the vector like this. And then what we have to do is to calculate HT of the next stage. First, start with H multiplying with the X, right? 1, 0, 0, 0, multiply with WXH, and then add to WHH times the values here. Then we get the new value at the next iteration. And then we can use this and then multiply it in here as well to jump into the next iteration. And each of these can be then translated into the output. It can be then be translated into the output by multiplying the hidden state with the WHY. It will transform into this vector, which will tell you that after H, it should be E, right? Because this is the result of the sampling. And then afterward, it should be each word here. But these are like the output that it should be. But you can see that the highest one is not that. The highest one is down here. The highest one is elsewhere. That can happen because these are the laws that I'm talking about. That, okay, the highest one should be the green one, but it's not. Then that means the network, when you train it, put the loss function and then move it backward, it will have to adapt W accordingly. Okay, but this is how it works in forward prediction and back propagation. Okay, so that means forward prediction has to be done step by step, iteration by iteration. And backward propagation as well, start at the end and then move back step by step. Now imagine, right now we have like 4,000, if we think about word that model produce, we are talking about something like a 10,000 window, 10,000 token that it has to move backward. Can it do that? Right? Context window is very large. So that means probably not work. But well, you see in work in a way. If you have very limited number of variability in tokens, then it will work somehow. Right? And that doesn't mean that this model doesn't work. This model is very basic. Although it requires quite a lot of time in training, but the model itself is really lightweight. It can be applied to do generation in other tasks. Might not be for language though. Okay, so when you learn about these things in this class, it doesn't mean that it doesn't work, then throw it away. Right? You might be able to use it to generate auto sequence that do not have quite complicated variation. And the model itself is quite lightweight. That means you can embed it into device. Because you can see that this is just a matter of matrix multiplication. If it can capture a certain pattern to use, then do so. Don't have to use the complex one. Or you don't have to use LM or VLM, very large language model, to solve the problem that can be done with just a simple RNN. Right, so RNN is still useful if the variability of the pattern is not that high. Okay. All right. So when producing the output, one token coming in, you get output layer. This output layer will then be converted into the softmax, and then from this softmax, the sampling process will be done. It will sample, not picking the highest one, although the highest one might be picked based on the probability. Softmax will convert from the real value into a types of probability distribution. Right? Highest value will have high chance to be sampled, lower value will have lower chance to be sampled. And then you can do just a normal sampling. Think of it as cumulative distribution. Do you know how to sampling? So from this one, you can then arrange it into CDF. You will have this, and then start with this, and then going with the second one and the third one, then here and here, like that. And then from this, you can then random, right, using RAN, do uniform sampling. Then you would have higher chance to hit this one more than this range. You have higher chance to hit this more than the others. This is how you do the sampling. In Python, in a lot of programming language, it is actually implemented in forms of the sample function for the distribution, I believe. Right? Then it kind of use normal uniform distribution and then uniform distribution from random generator and then map it to the inverse CDF, right, to get the value that you want. But because this is your own, that means sampling will have to be done accordingly, and then you will get the sample. Then for this one, then we will use the sample to be the new input. And that new input will be presented to hidden layer, calculate again, get output layer, do a softmax again, and then you have the token. So this is what it means by language model is basically the next token prediction, because what it remember, it would be what should be the next token to generate. Okay. And then once everything's done, then we have loss function. This loss function will then have to be updated, propagate to time. But just look at this diagram. There are quite a lot of backward propagation to time already. And it will create a problem of what? The exploding, right? Exploding because you propagate to time back, That means if the multiplication exploding, yeah, if it's like always more than 1 by 1%, then it will be too large to when you propagate it too many times. Same go for propagating back if the weight when that you multiplying has magnitude lower than 1, then you get the problem of vanishing gradient. That the gradient will have problem in there, right? So back then, in order to avoid this, one can do is to set up the windows. That means the model will just remember this much tokens. Nowadays, this is called context window. But back then it was like, okay, this is truncated back propagation. They just have window. But you can see the same concept being reused in today work now. And then you have like multiple layer doing it 1 by 1, backpropagate to just in that sequence. Okay, LSTM will come afterward to solve this problem, but later on. I'm not using Shakespeare though. Actually, Shakespeare is a good example to generate in RNN because we are not familiar with the text. Like it uses very strange language when you look at today's standard of writing, right? So for the model to be able to produce that, it's great. Right? But I didn't use it. I used the Wikipedia dump, and then use that Wikipedia dump with Markdown, and then trying to train those together. You can test it with anything, but because the model is quite limited, RNN is quite limited in terms of its capability. So just let's look at how it works there instead of expecting it to be more than that. Okay, so the idea is that at the first iteration, it will produce like non-language. This is not word by word though. It's more of if I remember correctly from the book, this one, this example is bigram or trigram, right, of the character, 3 characters at a time, and then doing that, and then to see if which combination would be more suitable and train more and more down there, and later on it'll be great. For the one that I did, I didn't use the trigram or bigram though. I just do the character level. We will see about that. And it is also able to replicate the paragraph style, having people who are talking and generate the story out. It has been tested in quite many ways. This is the live data set, that's open source geometry book. I think it was used to train the RNN LSTM model, and then it is able to produce quite, from far away, quite math, right? But from the closer look, all the garbage hallucination, right? So yeah, but still looks math in a way, or no? but yeah, look quite complicated. And this is from Linux Torvald, Linux repository. It is able to generate C code and also generate the heading that it should have. And so that's very early things that we have nowadays. Now, RNN alone is not that good. Okay, there are a variety of RNN that allow you to capture different contexts. For example, this is bidirectional RNN. You have RNN going forward and edged here, and then RNN going backward to capture the 2 dependency. Why would we do that? Because in RNN going forward, your assumption is only that previous state would influence the next state. But in reality, in language, it has been known for quite a long time that is not true. Because when you write and when you speak, sometimes you have initial word, it doesn't tell what would be the last word. Sometimes the last word going back to enforce what should be the earlier one. For example, if you know that this is a question, right, this is a question, then the structure of the sentence will have to be question. So it has to be what, why, when, right? And then following by verb to be. Why is something happen, right? So that means the question mark at the end might lead back to the structure. This is called, I think, this is called anticipatory effect. Anticipatory means you can anticipate if thing will happen in speech as well. There are anticipatory effects. And the other is co-articulation in speech, and in word here it would be like by forward progress there. But never mind, right? So you see the point, right? That there might be two-way encoding. That is why this is one of the reasons why transformer is so good, right? Because transformer allow you to ditch all this sequential dependency, and then you can have the mapping based on the attention mechanism, right? You can have saying that which token would depend on which, right? Not sequential that the next one depending on only the earlier one. Okay. You can have RNN in layers, and this will be the depth, right? The deeper version. When you have RNN in multiple layers, model will be able to remember pattern in quite more complicated way. For the LSTM, in the LSTM, there are, this is the equation for LSTM. So there are different, they call so-called gate, that is used to representing different things. Let's look at LSTM later on. This is the gradient flow for vanilla RNN. You have HT and XT stacked together, multiplied by W, and then you have HT. So the equation representing it would be this, right? Adding them together, which equals to stacking them and stacking them. And think about that as dot product of the vector. And combining it, you have just W passing through tan H. Gradient would flow back. Right? Gradient would flow back, pass through W. So it depends on W transpose. The norm, right, the size of W transpose for it to, because it has to pass through many states, right? Pass through many states. If the singular value of W, right, singular value indicate the singular value of a matrix indicate the magnitude of transformation. If the singular value, just like if you study this in computer graphics, if you have a singular value of a matrix, transformation matrix, multiplying a point of, say, the box, if it's large, then the volume inside will increase according to the singular value. Think of it as just like scaling vector of the magnitude of the coordination of the representation. So if it is more than one, then you encounter the problem of exploding gradient, because gradient flowing back, it will be amplified every step backward. So at the end, it will be quite large. And same goes if it is less than one, then you have a problem of vanishing gradient. Okay, so this is the problem with the vanilla RNN gradient flow. Okay, sometimes this can be solved by doing the gradient clipping, but it doesn't solve the vanishing gradient problem. There are some way to solve, though, people trying to replace tan H with other things so that it has less problem with gradient, vanishing gradient, like replace it with Lelu and others. But still, if you use just vanilla RNN, this will be a problem. Change the architecture to LSTM. In LSTM, it works in this way. Instead of having just HT, you have both HT and CT to represent the state vector. And HT and CT will work according to the above, right? The CT come from F dot CT minus 1, the previous state, and I dot with G, right? And HT come from taking CT, passing through activation function, and then multiply with the output. Okay, there are reasons how this works. Each of these, FIGO stands for different things. This is from 1997, back very long time ago, to solve this problem. This year is 386, I think, 486, the computer at that year. Right? 486, about Pentium 1, the year of that. Yeah, I think it's Pentium 1, Pentium 2 back then, not at the current computation power yet. Well, FIGO, right? Forget gate. Right? Forget gate here we will learn whether you would want to forget the cell or not, right? To erase the memory. Or skip, think about it's like whether you want to skip the multiplication at that state and going to the next one or not. That's the forget gate. Input gate determine whether you want to write to cell or not. Gate here on how much to write to the cell, and the output gate is how much you want to review. Okay. When it is perform computation, you have a large W and then X and H stacked together. And after multiplication, then we will have like sigmoid, and tan H. And as you know, the tan H, sigmoid looks like this. Sigmoid would be 0 and 1. Right? This is sigmoid. The range of output here would be 0 to 1. Actually, it's not. It's about here. Sorry. 0 to 1. This is sigmoid. Tan H will look like this, if I remember correctly. It will range the value to be real value, positive, negative. So now if you think about this is like a switch, turning on and turning off. Right? So IFO are the turning on and turning off switch, while G, the gate here, would represent on the transformation to that domain. And how we use it here, F, right? F here, and when you calculate CT, then you multiply CT minus 1 with F. What is F? F is forget gate. If F becomes 0, or multiplication make it low value, it will depend less on the previous step. So that's why it's called forget gate. Would you like to forget the past? Just use the current value. And then I here input, right? Input, and then I time with, I think there's this. I would time with G, okay? And then X and H stack together, multiply with W, and then for this I time with G, and then it will add to the CT minus 1, right, to be the new CT. Like F is forget gate. If F is 1, say you have CT minus 1, add to I and G, and then you have the current state. With the current state passing tan H, with O here, you have the new H. Okay, so these are the roles according to this one. Right? So the new state, depending on I and G, right? And the output HT, the state, hidden state here, depends on O, right? What is O? O output gate, how much you want to review to that cell. That means if O is 0, right? If O is 0, HT will be what? You get this, right? And then if O X is, because if O is 0, then H would be low value somehow. C still carry on continuously. Right? So you have like 2 channels of memory. Right? That one is long-term memory, the C channel, and another is the short-term memory, the S channel. And then it kind of go together. That's why it's called long short-term memory, and combining together. Right, there is like direct channel propagation from the output from C, uninterrupted gradient flow. And there are other variant of RNN as well, the GRU and other network that proposed back then. Right now, um, everyone go for transformer because these LSTM, well, LSTM are still useful though. Don't just throw them away. Sequential model are still okay if the problem is not that complex and you have really token state-by-state dependency. This is still okay. But if you know that there are all-to-all contextual dependency, like in word dependency, then that's the time for transformer. And that's why language model now use transformer. Okay. Because sequential model has bottleneck, right? We have compute H5, you must compute H4, H3, H2, H1. We are not even talk about H500 that you have to propagate everything back. You cannot skip step, you cannot parallelize, make it very slow, right? Both in training and in prediction. Okay. But if pattern is simple, it's fine. Okay, this is one problem. Another is in terms of memory compression. Because all the history, everything must be stored in just HT. Imagine that everything will have to be stored in this vector, right, in this transitional vector. So how complicated this have to be in order to accommodate all the patterns? It will be quite large, and the size will have to be fixed because you want to, it has to compress to just this one. So there will always be information lost there. So that's why in the later model, always shift through attention, because instead of compress everything to just one vector, you can have attention, and then have different multiple version, multiple vector depending on one another. All right, so that's the summary. In RNN, it's recursive. LSTM work as gate attention. Then you have the token-token associations. Okay. Another thing that is good in terms of attention comparing to RNN, when in RNN, dependency of token 1 and token 100 are tied together, right? Token 100 depend on token 1, and the update of token 1 depend on token 100. Right? So gradient have to be multiplied many times. But in attention, you have just one step. The path length is just one. You have then dependency. Okay, so it's a lot faster, right? More efficient. Okay, so LSTM is okay. It's fixed gradient problem, but it's still not fixed the still sequential, still have fixed size, and use quite low GPU. You can utilize GPU quite less because to be able to use GPU effectively, you need to be able to multiply things. Right? GPU work well with GPU multiplication. If you can multiply metrics together, not GPU multiplication, sorry, matrix multiplication. If you can multiply the matrix together, it works. Right? So you have to be fast, you have to be able to decompose and multiply metrics so that it works. And that in the latter part, we will see the other model, like sequence-to-sequence attention and then transformer later on. Which it still does this. It's still trying to represent P of the XT given the previous token, still solving the same problem, but with different perspective. Like rather than do solve things sequential way, right, it will be what should it attend to, right? So transforming from the current, that's why it's called transformer, right? Transforming from the current sequence to the next sequence, right? What transformation should occur? So that's the transformer. Right? Transform from one version to another version. Let's look at the lab. I thought I'd make it like all right. So the first example would be vanilla RNN, and then the second one would be LSTM. For both of them, I use Wikipedia dataset to train the model. Not here yet. But because Colab has this pre-install, not pre-install, right? Pre-install Kaggle dataset, we will use the one that is already in Colab, right? For that. Okay, so initialize that to get to know that we use GPU here. Let me zoom in. And this is the part, it's Kaggle input wiki text to dash data and train.txt. Right, let's look at here. Oops. Oh, no. Let me check. Did they change the version somehow that I don't know? Let me check first. Right, there should be, shouldn't there? Nothing here at all. I don't know what happened though, because during the time of preparation still work. This supposed to happen, right? When you present something and it will not stop working at that time. But I don't know where they moved this off, because I just used it last week, week before last week when preparing for the lecture. Open the Google Colab. Oh, you can't? Okay, let me share that. But I did share the link. Can you access it now? They are the same though. Yeah. It should be. Can you access it? Other? You can, right? Let's try. Let's try restart. I don't know. They might have refreshed the runtime, remove every test data out. Shouldn't do that. Let me check. Okay. It should be there. No, it's not there. You can actually go to Kaggle and then download Wikitext to dash data, and then you have train.txt to use that. Right. Let me try to do that. Train. Okay. Easiest way would be just to download it. I can use this. Put it there. Or I can just download and put it over there. Work similarly. Archive. Here. Upload file. Archive. Train. Ensure your file are safe elsewhere. Okay. Right, we still have 5 minutes to wait. Let's chill. Let's chill and wait. And your lab, your task will be doing things similarly. I think I will brief you on that later on. But for now, let's wait a bit, and I will go through the architecture. I have to tell you this though that the design choice that I use is not quite great. I created very basic RNN. That means the number of states is, I think, too low. And there is only like one layer. So usually you kind of need multiple layers for it to remember things out. But I just want to show you that very simple setting also work more or less. Right, so let's wait and do that. In the meantime, do you have any question you would like to ask online as well? During the wait, if you have any questions, please ask. And outside as well, if you have any question, please ask. I will reiterate your question so that people online can hear. Nowadays, you are hardly you will hardly have chances to train from scratch like that because there are already pre-trained models that are quite powerful. Right? What you would do would be to use those pre-trained models, fine-tuning it, still costly, still quite a lot computation. Or maybe creating additional weight like what we learned in last time in LoRa, right? And adding it to work beside fine-tune, that might work. Right? So there are those ways. Or creating multiple layer of architecture so that your model will be combined with, say, other more specialized one. Right? You have cache version, you have other context to combine with. Right? Let's continue. Okay, here I already initialized Tesla T4, and this is the one that I downloaded from Wikipedia. This is New York FC season, and this is in Wikipedia style. in Markdown style in Wikipedia. UNK mean unknown. So cleaning here will replace all the smaller case UNK with just UNK and replacing /r/n with /n. Then clean up all the whole text. And here you can set up the max character on what max character that you want. You can increase the max character. That means the text will be captured in this to be used to train. Then split them to 10 test bit at the end. And but you can increase as well to use like the whole corpus. This is just to demonstration, so I will not use the whole things. Then build character vocab from that. For now, we have 134 characters because we are doing it in character level. Then encode the character to integer, not in the, oh, how come Tosh is not defined? Thought I already run the first one. Oh, haven't done that. I will run it in the, suppose in the new setting. Okay. Should be fine now, right? We can convert it to Tosh. And then this is the char chunk to, instead of predicting in one by one, create a chunk of character instead. So this chunk of character will separate the data into chunk, and then what we are trying to do is to do the next char chunk prediction. Here defining data loader to load the model with a certain batch size. And then it comes to the character RNN and character LSTM. So I should close it down. The architecture of character RNN, still we have embedding as well to do embedding at the lower dimension. And then at this. And then you have input size and then hidden size in the RNN. You can see that we just have one RNN and one linear layer. Just that, so it will not be able to remember quite a lot. Hidden layer dimension is 256. Then we have a little bit of dropout here. And for LSTM, we're replacing everything with LSTM. Then we will have this number of million parameters. RNN is quite simple. You have about 281,000, 0.28 million. Of LSTM, you have about 1 million parameters. Then we can evaluate the model through the loss and perplexity. I think did I incorporate the perplexity calculation here? No. I should have, actually. I have the slide on perplexity, but not here. Maybe next time then I will put the equation on perplexity to look at, because it is used to evaluate the language model in terms of the ability to generate variation that is consistent to the real text. Right? We look at perplexity. Okay, and this is to evaluate that. The first one, loss, we use the cross entropy to calculate the loss, and then the PPL here is exponential of the loss. You get perplexity. And then here's the training loop defined as going through multiple epochs and then train. And then we perform a zero grad, moving forward with the model, and then calculate loss through the cross entropy, and then using loss to step backward. So similar to what we did in the previous all the previous lectures. Right? We would push the input through the forward pass, and then from the forward pass, calculate loss, then use backward to do back propagation. This is to ensure that there's no gradient problem there. Then step to update the parameters, so on, calculate the loss there. And then also keep track of the perplexity. It will take a while. This will take a while. And this function is to generate text to sampling from the data. So what it will do is to move forward, right, last ID and the hidden, to get the hidden and the logit, and from the logit then sampling it to get the token, and then convert it into the item, and then move the next ID to last ID, and then repeat the loop to get the prediction. So this is how it's done, that to predict one token at a time. Then join them together to have as output. And then here is the training, just train model and then see the result. It will take a while, quite slow here. Each step, this will show you the loss function, loss value. You have perplexity and the loss and the sample output. Okay, because we, instead of training character by character, we are training them as chunk, right? That means the word will look closer to the real thing, but not real English. You can see that the first iteration, you can hardly understand what is said here, not like the real things. But second one, you can see that because we use chunk, there are some of the remnant that are still there. Okay, so it makes it looks like the real thing here. And if you look at the loss reduced from training from 3.3 to 2.5 to 2.3, 2.2. You have something like South Wales, don't know what it is, and then looks more like human text. Okay, move through that. I think I set it as 20 epoch, if I remember correctly. Yes, here. Disproportionately, still the text are still wrong, but you can see that the structure starts to make sense, more or less. This is for RNN. And last, after 20 epoch, we have validation loss of 1.7, validation complexity of 5.75. This is for LSTM 20 epoch as well. Okay. Okay, let's wait for a while. But what I show you here is very basic and not work in real life, but at least it will show you that this is how sequential model works. That is, when you train it, it encodes into the hidden state, just the hidden state. But with just the hidden state, it can also predict more or less the strategy. If you give it more time, it will be able to remember quite a lot more and quite convincing output. It can hallucinate to the quite convincing output for that. Here is done already. We have this is the training loss, validation loss, comparing the two, which is actually not comparable yet because this is like very early stage, but you can see here's how you compare it more or less. With the seed here, history, geography, biography, and then we said I should generate 400 token out and give it the top K. And then let's see what would it look like compared to result. History, right? Don't understand any of these for both of them. Right? Geography, biography, in artificial intelligence. Are there any word that hit the AI? No, probably not related to song. But well, you can try training this longer than what I show you here. Thailand is, and this much, what? It probably say that this March will be the top. So if you, not the financial advice, no, this March is a top, right? Uh, Whatever that. So that's the character chunk. Now let's look at the word level. Again, I need to. Actually, I don't have to run this because, but in any case, I can just change this to content. Again, doing the same thing, make it more. Tokenization. Using word require tokenization. That is, you need to split. You need to split the word into tokens, and then you will represent the tokens with embedding. Okay, and this is the token that we use. Vocab size is 28,000 words. Then we encode the token. And then these are, again, word chunk. Let's just train the model. Okay, word level language model here. Still the same structure, just one RNN, and I think I just only demonstrate LSTM, just the LSTM and the embedding. A better way would be to use the pre-trained embedding, and then you can fine-tune the pre-trained embedding afterward, but I didn't use that. You can put it, I think you can take it from GenSimos, so the pre-trained embedding for that. But I just use the embedding here. Now parameter will become 25 million. Let's train the model. The rest are the same. So this is how sequential model work. Right? In sequence model, you encode the representation in terms of the state transition, and also the transformation of input to the state. And then you also have the translation from the state to output. Right? So combining all of those, you have sequence model. Okay, this is from one epoch. How many epoch? Still 20 epoch. Let's wait for a moment and see what we have at the end. But because we use token level, the word will be words based on the token, and then it will be the next word prediction. That is try to predict. Problem with this way would be that you don't have the ability for it to remember the new word or generate the sequence that is not in the vocabulary. But we just try to simplify things here. A lot of conjunction though that it generates out, still not like the real word here. I don't know if we will have enough time, like 20 epoch, to make it and wait for it to learn everything. Maybe not. So, but in any case, this is the architecture of it and how it works, right? Still no keyword that are relating to the seed that we have. But anyway, in any case, you can wait and then see if the result would look like that later on. Maybe for now, let's look at what lab that you have to do in order to kind of catch up and then experiment with the work here. Why? You can come up and then showing the work that that the student have to do. At first, PY said whether we should kind of combine this RNN, which doesn't work well, with the transformer entirely, but I think you should experience this a bit, right? The slowness and it works, but not work, right? How it works there. All right, so why you can come here and then brief that to everyone.
Okay, so for the work that you have to do in the lab is similar to what Ajahn Yai just demonstrated to you. So I want you to train the simple text generation model using this dataset that I provided to you in LEB2. So let me walk you through this dataset first. So this dataset is the Sherlock Holmes novel dataset, which consists of 4 files. If you download the dataset and then extract it, you will have this folder called Sherlock Holmes novel. And inside you will have 4 files, which are the novels of the Sherlock Holmes, starting from the Study in Scarlet until the Valley of Fear. So I want you to use these 4 files to train a just simple text generation model. You can use any architecture that you want, but just provide a short description of how you design, how you prepare the dataset in order to build the model.
If you want the model to remember better, maybe you can try stack them, find it.
Yeah, you can use any design that you want. And after you train the model from the part 1, part 2 is just I give you a prompt and I want you to just play with the model that you have trained. So I have prompt, I provide these 10 prompts for you to just try to how the model will respond to each prompt.
The chance that each of you will have the same result
is pretty low.
Pretty low.
Yeah.
And is it group work?
Yes, it's group work.
It is group work.
Okay, so this is just part 2. Just put this in the text generation and just capture the result. It doesn't have to be long though, just like 50 or 100 character is fine. And for the part 3 is just a question. So just answer this following question.
Right, it is group work, right? As I said the other side that the chance that you get the same result will be very low. And you can explore architecture as much as you like. You can try bidirectional LSTM. You can try just RNN or LSTM in the stack layers. It provides better result, but it takes resource as well, okay, to run that.
Just keep it a sequence model though. Don't try the transformer one yet.
Yeah. Transformer will be next time. So that you see that, oh, it's a lot better than the sequential one. All right. Okay. Yeah, thank you. So for now, the training that I'm still trying to wait for this to be done, still not have the good word related to the keyword yet. History still produce something that like relate to series, relate to episode, right? And Thailand has the word city. So it now has something related to geolocation, but I don't know something about song. This is like in the running file that I'm waiting here. And artificial intelligence is now a club, with season 3, something related to the world, whatever. and also British something as well. So that takes a lot more time to wait for that. In any case, Sherlock Holmes is good because it is quite specific. And so do you expect them to do at the character level or the word level? Right, so you can do it in the character level, in chunk, trigram, subword levels. Subword level means you don't have to explore all of the word. You can use one hot vector and then train it with that. Or you can do the word level as well, using embedding like that, and then trying to find that. If you use, but if it will be fascinating if you use character level, because you will see from the very bad output, it will gradually transforming into Sherlock Holmes, that in the gradual way, that in the early part it produced nonsense syntax, and then in the latter part it will be better. Okay, so that's the generative sequence model for this week. I hope you go back and then try work on that in group. The next time we will look at the current, not really current, well, since the transformer-based model, we will look at the design of the GPT in the earlier version on how it works, because in order to create that from scratch is quite a lot more challenging. So we will try to use, at least use transformer and then use the same data set and then trying to see whether it would produce a better result, faster convergence or not in a way. And we will use the pre-train and then try to use the pre-train to produce some small pre-train to produce, and you see that the output will be a lot better than the one that we already did training there, right? So that will be for the next time, okay? Okay, so for this week, let's call it a day. The next week is on the 9th, right? The 9th of March. We will have the class on the next week on the transformer-based model. And then we will skip for the subsequent one on the 16th. The 16th, I will not be in Thailand. I will have to go with the university to do some work abroad. So we will skip 16 and then seeing each other on 23rd. And so that means like 1 week skip on the 16th of March. Otherwise, we're still having the same schedule on, and it should be okay with what we already have. Sorry about last week. It turns out that activities are quite loud. Some of you are here already, and I hope you enjoyed it a little bit. Food, whatever they have activities down there. Okay. In any case, well, see you again next week, and enjoy sequence modeling. Although might not work for this week, it will work for the next one. In any case, and try your best and have fun. Right. See you again next week. All right, for the online session, I'm turning off. See you again next week, everyone.